Here's another rate problem, which I want to use to illustrate the relationship between the rate, the equation, and the graph. A phone company charges 20 cents per minute to talk, plus a 60-cent connection fee. First, how much will it cost to make a 7-minute phone call? Well, it's 20 cents per minute, so that's 20 times 7, plus the connection fee of 60 cents. That makes a total of 200 cents, which is $2. Next, how long can you talk for $5? Well, don't just divide by 20. That won't work. They're not in the same units yet, and there's a connection fee to take off as well. $5 is 500 cents, and if we take off the connection fee of 60 cents, that leaves us with 440 cents. Now, divide that by 20 cents per minute, and you'll get 22 minutes. You can talk for 22 minutes for $5. Actually, those questions were really just a warm-up to make sure you understood the problem. What I really want to ask you is this. Can you write an equation here relating the call cost to the length of time you talk? Well, what did we do in part A? We worked out the call cost by multiplying the rate by the number of minutes, and then adding the connection fee. The call cost is 20 times the call length, plus 60. Notice that structure. If you were to draw this relationship on a graph, would it go through the origin? What would the gradient be? What would the y-intercept be? So let's draw the graph now. How will we do that? Let's make a table of values that we can plot onto the graph. Choose some call lengths, and then calculate the costs of those calls. Even if your call lasts 0 minutes, you still have to pay the connection fee, 60 cents. For 1 minute, it's another 20 cents, 80 cents. For 2 minutes, it's another 20, and so on. Okay, let's draw the graph. The cost depends on the time. Plot the points. Draw a straight line. Did I actually need all those points? What's the minimum number of points I need? So, were you right? Does the line go through the origin? No, it doesn't. Why not? What does the y-intercept on this graph mean? What's the gradient? Choose 2 points on the line. Any 2 points will do. How far does the graph rise between these 2 points? It goes from 90 to 140, which is a rise of 50 cents. How far does it run? It goes from 1.5 to 4, a run of 2.5 minutes. Okay, so let's calculate the gradient, rise over run, which is 50 cents over 2.5 minutes. That's 20 cents per minute. 20 cents per minute. What does the gradient represent here? It's the rate at which the call is being charged. And what's the y-intercept? What's the value on the line at 0 minutes? It's 60 cents. And 60 cents is just the connection fee. So the gradient is the rate, and the y-intercept is the connection fee. Is that what you predicted? Have another look at the equation we wrote earlier. The call cost is 20 times the call length plus 60. Look again. The dependent variable is equal to the gradient times the independent variable plus the y-intercept. This is always the structure of an equation that represents a linear relationship. Another example just like that one. A taxi company charges a $3 flagfall fee plus $1.10 per kilometre travelled. You get charged $3 just to get into the taxi, plus another $1.10 per kilometre. How much will it cost to travel 5 kilometres? Well, that's going to be $1.10 times 5 kilometres plus the $3 flagfall fee, a total of $8.50. How far can you travel for $20? Don't forget to take off the flagfall fee first before you divide. 20 minus 3 is $17. Then 17 divided by $1.10 is, how many decimal places do I need? Well, to be honest, if I'm in a taxi, probably the nearest 100 metres or so will do. So let's round off to 1 decimal place. 15.5 kilometres. Can you write this relationship as an equation? Look again at part A. We calculated the cost of the trip by multiplying the rate by the distance and then adding the flagfall. The trip cost is $1.10 times the distance plus $3. Notice that structure again. So, if you were going to draw this relationship on a graph, would it go through the origin? What would the gradient be? What would the y-intercept be? Let's do it. First, a table of values. Our variables are distance and cost the cost depends on the distance. Now, how many points do I need to work out? In fact, 2 points will do, but I recommend you always choose at least 3 points. That way, if you make a silly mistake, you can see it more easily because you won't get a straight line. So let's choose 3 distances and use nice numbers we can calculate with in our heads. A journey of 1 kilometre will cost the flagfall fee plus $1.10. That's $4.10. Each extra kilometre will cost another $1.10. Okay, plot the points and draw a straight line through them. Were you right that this graph doesn't go through the origin? Why doesn't it? What does the y-intercept represent? Let's calculate the gradient. Choose 2 points. Any 2 points on the line will do, but this line doesn't cross grid lines in nice places. So let's choose 2 points I can read off the graph easily. This section rises from $3 to $6.30, a rise of $3.30. The run is 3 kilometres. So the gradient, rise over run, is $3.30 over 3 kilometres, which is 1.1, $1.10 per kilometre. What does that value look like? Is it what you predicted? And the y-intercept, that's $3. Is that what you expected? The gradient is the rate, and the y-intercept is the flagfall amount. Let's go back to our equation. Trip cost equals $1.10 times distance plus $3. The dependent variable is equal to the gradient times the independent variable plus the y-intercept. Do you think you could go straight from the problem description to the equation without drawing a graph? Could you go from the graph to the equation without seeing the problem description?